Hello, welcome to the first lecture of our course, GE-151, Introduction to Materials of Engineering. Let's start by looking at the difference between materials science and materials engineering. In materials science, we're trying to gain a fundamental understanding of the reasons or the mechanisms as to why materials have certain properties. Often this involves looking at materials on a microscopic or even an atomic scale. In materials engineering, we wish to apply the knowledge gained through materials science activities to effectively developing new materials, processes and products. Materials science is an immensely important human endeavor, so much so that the development of our civilization has been measured in terms of the mastery of our materials, from the Stone Age to the Bronze Age to the Iron Age. Our mastery of materials has brought forth the modern world, and innovations in materials often enable technological advances. Such developments in materials affect us in many ways, and I think one of the most exciting ways is the way in which mastery of materials can enhance people's lives. And here we have an example of the use of various high technology materials such as metals and alloys, polymers, to produce a lifelike prosthetic arm. A common theme in materials is the interplay between the composition of a material and its structure, how that relates to how it must be processed, which gives rise to particular properties which relates to the performance of the material in a particular application. And all these things are interrelated. Materials may be classified according to their composition and structure. If we do that, we can see that there are 5 important classes of materials. There are metals, ceramics and glasses, polymers, semiconductors, and if we combine some of the aforementioned groups, we can get composite materials. Let's have a look at each in some detail. Metals. Metals are characterized by good electrical and thermal conductivity. They can be shaped by the application of force. They are strong and stiff. They have medium temperature performance and are impact resistant. Ceramics, glasses and glass ceramics are formed from inorganic compounds. Ceramics have a crystalline structure, whereas glasses have what is known as an amorphous structure, where the atoms are randomly orientated. Ceramics and glasses generally do not conduct electricity, and some of the best insulators are ceramic and glass materials. They are strong and hard, but these properties also lead the ceramics and glasses to be brittle, which means that small cracks can grow and propagate and to cause fracture of the material. They have a high temperature performance, but a downside to ceramics and glass is that they can be hard to shape into precise forms. Polymers are formed from organic molecules, carbon-based molecules, that have been processed to form long, complex chains. They have low densities, but can have good strength-to-weight ratios. One thing that's not mentioned here is that a number of polymers are chemically inert and have excellent environmental resistance to environmental stresses. such as corrosion. Many types of polymers are resistant to impact, and polymers, often called plastics, are easy to form, the name plastic meaning to shape or form. And they are very good electrical and thermal insulators. Semiconductors are a special class of materials that are found in electronic devices. Examples of semiconductors are silicon, germanium, and gallium arsenide. They are mostly found used in single crystal form. The materials are produced to a high purity, but they are deliberately doped with small quantities of foreign atoms to give them the electronic properties that we desire. However, amorphous silicon is also an important material for solar panels. Composites. With composites, we marry two types of materials from the metal, polymer, or ceramic glass group to create a material with superior performance. Some everyday examples of composites include concrete, and glass fiber reinforced composites are common parts of car bodies these days. Carbon fiber is used in very high-tech applications such as aerospace. There are also carbon-carbon composites. Again, these are expensive high-tech applications. Carbon-carbon composites have been used to create high temperature resistance or high performance brake rotors. Our bodies are composites. For instance, our bones are ceramic polymer composites, where the ceramic is hydroxyapatite and the polymer matrix is collagen. Wood is a polymer-polymer composite formed of strong, hard cellulose fibers embedded in lignin. And this nautilus shell is an example of a natural ceramic polymer composite. Again, hydroxyapatite being the ceramic. Materials may also be classified according to their function. In this case, we can mix materials with different structures and compositions into the same group. For example, here we have the aerospace group, in which has been some examples of materials that are in that group are carbon-carbon composites, silicon oxide, amorphous silicon, aluminum alloys, superalloys, which are iron-nickel alloys that can withstand high temperatures. Examples of functional classifications include aerospace, biomedical, electronic materials, energy technology and environmental, magnetic materials, optical, smart materials. Smart materials are materials, one example of a smart material is a material that can retain memory of a shape. So it can be formed in a particular shape. If it is deformed, the material can be processed, perhaps by heating, in such a way that it will regain its original shape. And of course, structural materials. Let's practice classifying materials. Let's have a look at this house in construction. And we can see a number of materials being used here. We have the wood, which is a natural composite or a natural material. We can see here the concrete foundation, which is a ceramic composite. We can see some rebar here, metal, and looks like perhaps this is insulation here, which would be a glass fiber material. Here we see a hip replacement component. This part here, the stem, which is embedded into the top of the femur, is made out of titanium. The bearing here is made out of a polymer. Here we see a disassembled iPhone, and we can see a large variety of materials, from the ceramic glass front, which is here the material is chosen because, of course, glass is for its clarity, in terms of allowing light. It allows light through, but also that is scratch resistant. Here we use the property of ceramics being very hard to provide excellent scratch resistance to the top of the phone here. But of course, for anybody who's dropped their phone on a hard surface, the brittleness of the glass material is evident. In the electronics, we can see electronic materials. We can see various polymers being used for various components, metals for screws. We have energy technology materials being used in the battery. We have a metal frame. We have optical materials inside the camera. So there's a large number of materials being used inside the cell phone. A growing an important issue now with the use of materials is looking at the product life cycle. In the past, designers concentrated on the design and production, packaging and distribution and use, but the end of life was not considered. This has led to environmental problems of discarded equipment or discarded consumer goods and pollution. So now we need to look at the materials that we use for a particular product to ensure that we can close the loop, perhaps at the end of the life of the goods or the product, to ensure that either we can recover materials from the device that can go back into the cycle, or we can directly recycle components from the device, or put it back into reuse. The last resort is to dispose of the material in a landfill or incinerate it. In response to these considerations, there have been some very interesting innovations. One of them is to use mushrooms to grow or as a substitute for the foam inside some vehicle components. And you can follow a link to this video to see an interesting example of that. There are so many materials available to the designer that material selection is an important discipline in its own right. When we select a material, we have to take into consideration the mechanical or physical properties in terms of the performance of the component, the ease of manufacture of a particular material, the cost of the material, its aesthetics, its availability, any ecological considerations, its resistance to thermal stress and whether it be required to conduct heat or insulate, its corrosion resistance and compatibility with its operating environment. Will the material be exposed to vibration or cyclical loading? If it is, we need to ensure that the fatigue characteristics of the material are appropriate. And will the material be exposed to wear due to friction? So these are some of the important considerations that have to be made when selecting material for an engineering application. So that's it for part 1. I hope you enjoyed it. Thank you.